Hello everyone, and welcome to class number 1 for our falling mass rotating pulley experiment. So today here's what we're going to do. We're going to introduce the physical system, so I'll show you the setup, which involves a mass tied to a string that's wrapped around a pulley. And we'll start to think about what's going on. So to do that, we'll need to spend some time reviewing rotational dynamics and torque. I know 117 was a while ago, and this past semester in 117, we didn't get to spend as much time on rotational dynamics as ideally I would have liked to have. So I'll sort of use these ideas to build up for you an idealized model of this setup where we don't think about any frictional effects. What you're going to do in lab on Thursday is to try to work out a theory, a model for the setup where you do include those effects, and then we're going to think about sort of all the things that we might not be including in our idealized model, and either try and figure out how to either account for them or to put ourselves in a regime where those effects don't matter. So this is the falling mass rotating pulley setup. I've got it set up in fairly small scale using the big stand for the pendulum, and I've got it set up low so that I can get pretty much the entire thing in a single camera shot. Jill was so much better of a photographer than I am, so pardon me for that. So right now we've got this mass tied to a string, and I'll come up and show you what this mass hanger looks like in more detail. I just have a little sort of excess tag of string here off the end. There's a piece of blue tape on the pulley that's just keeping it from unwinding itself and crashing to the ground. But we have our pulley here, and if I take the tape off, it's free to rotate. There's a crossbar. The pulley's on a stick. I have the stick attached to this crossbar with some clamps. I've got some more clamps here for holding the photogate, but we won't need that just yet. Today we're just going to talk about the theory behind understanding this setup. So I'm holding here one of the plastic mass hangers. It's the same one that I have tied to the string on the setup behind me. It's just a little piece of plastic, really. It's got a little hook here, which is where I've tied the string. There's this post that you can string these masses onto. So I'm holding this one, says it's a 20-gram mass. So if I put that there, and I tie a string to this, that's what I'm dealing with over here. So if I zoom in for you there, you're seeing the pulley. I'll zoom out. You can see the string hanging down, and there's my mass. And if I sort of aim the camera towards the ground and zoom out some more, I think you can see most of the setup. Let's just stop that. Now, one of the things you can do is you can imagine comparing what happens if I were to take off the tape and drop this mass and drop another object. So you know that near the surface of the Earth, things fall with the same free fall acceleration regardless of their mass. And so if this were to be in free fall after I take the tape off, well, you'd expect that if I release the hanging mass and this marker at the same time, they'd hit the ground at the same time. But does that actually happen? Let's find out and see. I'm just going to arrange this cloth here so I don't bang the mass into the floor. So I think you can still probably hear a thud when it lands, and you can see what happens. I'm going to take the tape off. We'll see if this works. So I've got the mass of my marker here at about the same height. And then when we say 3, 2, 1, go, I'm going to let them both go. And we'll see which hits the ground first. So 3, 2, 1, go. Now, we might have to slow things down to see what happened, and it's hard to see because I'm not dropping this over a very large distance here. But maybe you could argue that you can maybe see that the marker actually hit the ground first. Why is that? Well, probably the obvious thing, right, is that we have this pulley here. And our job for today, in fact, is going to be to think about what that does to the physics here and why this mass with a string wrapped around the pulley does not fall at the free fall acceleration. First of all, a few reminders about some things in rotational kinematics. That is how we mathematically describe rotations that are worth remembering. We'll just consider this, for sake of argument, some sort of rotating object. So I'll imagine a wheel that's sort of on an axle where it's spinning around its center. And let me imagine that I make a mark on that wheel so that I can see the orientation of the wheel. What we need in kinematics is, we can describe the orientation of the wheel by the angle theta, like that reference mark makes with some original position or some original angle. Let me define, so if I were to redraw this at some other angle, the mark might look like this, and then I could define my angle theta relative to the original orientation when that green line was horizontal. Now, angles, we need a convention to talk about whether they're positive or negative. The typical convention, and what I will take here, is I will take the counterclockwise direction, or if you're British, the anti-clockwise direction, to be the direction of positive angles. So here I've drawn a rotation in the positive theta direction. Now, so this is analogous to in linear 1D kinematics. The angle theta here is analogous. Let me use a different color. Let's see, red. Okay. This is analogous to the position x of a point particle moving in 1D. Now, sort of pushing from sort of what you remember about kinematics from 117, we defined position first, and then we defined velocity, and specifically the x component of velocity, d sub x, and that's just dx dt. In the same way, we can define sort of the rotational analog of velocity by taking the time derivative of the angle theta, and that is in fact what we do. We have the angular velocity, and we give that the symbol Greek letter omega, and that we define as d theta dt. Now, a word about signs. So you know that velocity truly is a vector, but if you're working in 1D, you can just get away with thinking about one component of the velocity. So if you're thinking about just like the x component of velocity, you can have a positive x component for motion in the plus x direction, or negative for motion in the minus x direction. Now, in advanced mechanics, you'll talk about more the sort of the truly vector nature of angular velocity. That's a complication we don't have to worry about, since we're dealing with rotation of an object about a fixed axis. You sort of need the full vector treatment if you want to do something complicated, like let's say I have that, I drew a marker, and now, I had that marker tumbling about several axes simultaneously. I'm going to pause the video while I go get my markers back. Okay, so now that I have my markers back, we've just agreed that we can think about the angular velocity as a signed quantity. So to do that, right, so the omega is positive, right, if we have theta increasing with time. That is, if we have rotation in the counterclockwise direction. And the angular velocity is negative for a rotation in the clockwise direction. Alright, so we've talked about angular velocity, and the units of this, as you should remember from 117, are radians per second. We're generally going to think about rotational dynamics and kinematics quantities in terms of radian measure. So after we talked about velocity, right, the next thing we defined in 117 was acceleration. Right, here's my red marker. And so you know that the acceleration is the time derivative of the velocity. So we have ax equals dvx dt, giving us the x component of acceleration. And this one's a little trickier to think about, right, first in terms of signs. So is the velocity increasing or decreasing? So you can have a positive acceleration if something's like moving in the plus x direction and speeding up, or if something is moving in the minus x direction but slowing down. I mean, I'm not acting this out well for you, but hopefully that's something you remember from 117. If that's a little rusty, do take a look at your 117 textbook or notes, or let me know. I might be happy to point you to some resources for a refresher. Now, the same thing applies to let me use, this black. The same thing applies to rotations. I can get a rotational analog for acceleration by taking the time derivative of omega. So in that's angular acceleration. And we give that the Greek letter alpha, and we define that analogously as, I'll just do a regular equals. We define that as d omega dt. Once again, this is positive if if you have if a rotating object has got a positive omega and is like spinning faster and faster, or if it's got a negative omega and it's slowing down. So there's the same subtlety with signs as you have with linear acceleration. So this is also a plus or minus quantity. Okay, so those are the things that we need to remember for about the sort of fundamental quantities with rotational kinematics and how they're analogous to linear motion. We're going to keep pushing on this analogy between rotational and linear motion as we go forward. The next concept we need to remember is torque. So torque is to rotational dynamics what force is to linear dynamics. As you might remember, we can define torque in the following way. So torque always has to be defined relative to an origin. So I've labeled my origin with that dot in the middle. Imagine I've got like a bar or something here, and the bar is able to rotate about like a pivot right there. So torque is related to force. You need to have a force to have a torque. So let me imagine that I'm exerting a force, and it looks something like this. So what matters for torque is the force, its direction, as well as where that force is applied. So let me explain. So I can define what I call the r vector. So that goes from my origin to the point of application of my force. Okay. I can also define an angle, and I'll call it phi for now, an angle between my r vector and my force vector. And I have to be careful doing this because I need to put my vectors tail to tail. So let me draw a dotted line here. So let me just imagine a dotted line. I'm going to just redraw my r vector over here. So let me just draw that, something like that. My r redrawn, and then I define my angle phi between my r vector and my force vector. Now the torque is like everything else we've seen so far. We can think of this as a signed quantity. And it has the following magnitude and sign. So the magnitude we'll just do first. So the magnitude of the torque, and I'll write this as absolute value of the torque, is given by the magnitude of my r vector. Remember that the magnitude of a vector is its length times the magnitude of my force times the sine of the angle phi between my r and my f. So that gives me the magnitude, the direction, or the sign of the torque. So the sign is positive if it would cause a rotation in the positive direction, that is a counterclockwise rotation, and negative if it would cause a clockwise rotation. So here, if I'm pulling up on this bar and it can pivot like that, you can see, I think, that this force is going to tend to want to make the bar rotate like this, counterclockwise. So here, my torque is in fact positive. So a few things to notice, right? So what the dependencies, right? It depends certainly on the magnitude of r. So and you probably have an intuition for this if you've ever used a wrench or realize that you should like open a door by pushing it at the end and not right next to the hinges. It depends on r, it depends on the magnitude of the force, that's probably plausible. And then the angle, right? So again, the best way I think about it is think about opening a heavy door. You want to push right perpendicular to the door so that your phi is equal to 90 and sine phi goes to 1 so that you get the largest torque that you can. Now, you might remember from 117, I think we might have talked about it briefly, that torque really is a vector, and I can really think of this as a vector cross product. You may have started talking about cross products in 118 in the context of magnetic forces and magnetic fields. If you haven't yet, you probably will sooner or later. So I can technically, the proper way to write this, right, torque is really a vector and it's really this cross product R cross F. But again, since we're dealing just with fixed axis rotation, it turns out we really don't need this full cross product formalism, so it's okay to just think of torque as a signed quantity in this case. So we've defined torque, but then the question is, what does a torque do? Let me erase the board and I'll remind you of what a torque does. So the physics idea we need is something that people call different things. We might as well call it the Newton's second law for rotation. Now, you know what Newton's second law for linear motion says, right? So N2L, use a different color. For linear motion, and let's just keep this one-dimensional, you know that mass times the x component of acceleration is equal to the x component of the net force. The rotational analog of this says the following. It says that this thing called I times my angular acceleration alpha is equal to my net torque. So let me unpack this equation for you. So first of all, right, this I, this is called the moment of inertia. Or some people call it the rotational inertia. But whatever word you want to call it, this is sort of analogous to mass. For linear motion, but the functional dependence is more complicated. In general, right, if I have an object of mass m, its rotational inertia or its moment of inertia is going to be proportional to the mass times something about the size of the object squared. So if it's like a wheel and it has some radius r, it's going to always go like mr squared. And again, you can look up your 117 book if you want to remind yourself of the definition of moment of inertia and how it can be calculated. We'll just leave it as sort of proportional. There's a constant in front that depends on how the mass is distributed in the object. So you'll remember that you have different moments of inertia for, let's say, like a solid wheel versus a thin hoop or something like that. So our angular acceleration, that's our alpha here. We know what that is. We just talked about it. We also just talked about our torque, right? So net torque means add up all torques. Just like over here, F net x means add up all the forces that are acting on my object. So this, along with an appropriately drawn extended free body diagram, is going to be the basis by which we analyze everything having to do with rotations. The last piece of physics that I want to review, so it's going to be related to our setup. So imagine, so I've drawn our mass and pulley setup here, and as you let this thing go, right, the mass starts to fall and acquire a linear velocity, so it'll start moving downwards. And similarly, as you probably saw in the video, as this mass falls, the pulley is going to start rotating like that. So there's going to be an angular velocity clockwise. Now, here's the thing, right? It turns out that these two things are related to one another. So let me just label the radius of my pulley here let's assume that that pulley has a radius of little r. The idea is that if we assume that there's no slipping between the string and the pulley, then the following holds. So if string doesn't slip, right, what we have is then that the magnitude of vector v is going to be equal to r times the absolute value of my angular velocity omega. I'm writing this in terms of magnitudes right now. So in practice, you have to think about the signs that are involved, and you may have to put in a minus sign if you have, depending on the geometry of the problem and your coordinate system. And where this comes from, right, fundamentally comes down, it's like if I have no slipping, right, every time my block moves like by an amount that's equal to the circumference of my pulley, then my pulley is going to end up rotating exactly once. And again, there are some figures in Knight that I think explain this pretty well, but just think about, right, if I rotate this, maybe for me the easiest way to think about it is if a pulley rotates once, then like one circumference worth of string comes off. In general, if you rotate the pulley by an angle theta, right, so like arc length goes like r times theta, so you get like that arc length r theta coming off the pulley. You take the derivatives, and then that's where the r comes in between v and omega. It turns out if you take yet another derivative of this, you can similarly relate the linear acceleration and the angular acceleration. Also, my linear acceleration is my r times magnitude of my angular acceleration. So that's all the pieces we need. Let's dive into the analysis. Okay, so here's a sketch of our setup. I'm going to assume that the plus y direction is upwards. We have a block or a massive mass little m, and we have a pulley that has a moment of inertia I and a radius r. I haven't drawn it, but I assume that my pulley is like held up by some support like it is in the real experiment. So the first step in analyzing this is to draw a free body diagram for my mass m. So let's think about what's the forces, right? So maybe actually let's have you pause the video now, take a minute and think about what forces are acting on our mass, and think about you try to draw a free body diagram, and then come back and we'll see how I did it. Welcome back. So as you could have probably thought, there are exactly two forces that are acting on this mass, right? We have a contact force, there's a string here, so there's a tension force due to the string, and there's a non-contact gravitational force exerted by the Earth. So if I draw my mass as a dot, right, I know I have gravity acting down. So I'll label that F sub g, and then we have our tension acting up. Okay. We know that our mass is going to accelerate downward, so we know that from Newton's second law, the net force has got to point downwards, and that's why I drew this gravitational force vector longer than my tension. If we have our free body diagram, we can go ahead and apply Newton's second law. Okay, so Newton's second law says that MAY, the y component of acceleration, equals F net y. F net means add them all up, right? And we only have two forces. So we have the y component of tension plus the y component of gravity. Now remember that a vector component is both a magnitude and a direction, and sign, really. So here, it'll turn out to be convenient to write everything in terms of the magnitudes, but then we have to be careful about signs. Here, we know that we let this thing go, the mass falls, it falls down, it accelerates down. Because we've defined the plus y direction to be up, right, the y component of the acceleration is actually negative. So we actually have here m times minus the magnitude of acceleration on the left. Let's do the forces. Now the tension acts up in the plus y direction, so that's easy. But the gravitational force acts in the minus y direction. We know that this has a magnitude of m times little g, but we now need to remember the sign, right? So we have, because this acts in the minus y direction, we have minus mg here. This is really important, and it's really easy to mess these signs up, so take a moment and convince yourself that we've done this correctly. Okay, once again, let's think about the forces that are acting on the pulley. All the forces, and where they act. So again, pause the video now, think about it, and then hit play when you're ready. Okay, so there are three forces acting on our pulley. Right? So we know that the pulley has some mass, so there's got to be gravity acting on it. Right? So I'll draw that acting at the center, where the center of mass is. Right? We know that the string touches the pulley, right? So there's going to be some contact force by the pulley by the string on the pulley, and it turns out that tension effectively acts at the edge where the pulley and the string meet, or where the pulley starts to come off, and the string tension's gonna look something like this. I'm gonna counter it sideways. You draw that. My tension looks like that. Now, can these be the only two forces acting on my pulley? They can't. Because right now I have a net downwards force on my pulley, and we know the pulley is remaining fixed in space, such that, right, if a body isn't moving and doesn't move ever, right, we know that there's gotta be zero acceleration and then zero net force. So there actually has to be a contact force, I'll label it as a normal force, by the support shaft on the pulley, so I'll label that as a normal force F sub normal, and here F net is 0. So we're going to apply the rotational analog of Newton's second law here. This looks like it might be tricky to do, but it turns out that we're helped because only one of these forces exerts a non-zero torque about the axis of rotation. So then axle So if we apply the Newton's second law for rotation here, right, we have that I alpha equals net torque, right? So I have to think about whether which of these forces could exert a torque, right? My normal force acts right at the axis of rotation. So it has an R of 0, hence no torque. Similarly, gravity also acts at the rotation axis at the center, so R equals 0, no torque. For our tension, though, we have, right, our R vector is non-zero. It runs from the axle to the edge. It's got a magnitude of R, and lo, right, these two vectors are perpendicular, so the sine of phi is 90. So sorry, phi is 90, so the sine of phi is 1. So now we just have to be careful about directions, right? So this is going to start spinning faster and faster in the clockwise direction, which means that the angular acceleration is negative. So I'll write this as minus I times the magnitude of my angular acceleration. So it speeds up. Similarly, if we think about the torque, right, the net torque is only the torque due to the tension here. That gives me my magnitude of R is just the pulley radius R. I have my magnitude of tension force, and then I have a sine of 90 degrees, which is 1. I have to be careful about the sign though, right, because this torque tends to cause a rotation in the negative direction, so I actually need to put in a minus sign here. I have minus signs on both sides, so this actually simplifies to I alpha equals R times tension. So this is the second equation we need. Alright, I is something we can measure or look up or calculate. The unknowns here, right, we don't know the acceleration, we don't know the tension, and we don't know the angular acceleration. We have 3 unknowns and only 2 equations, so we need to close it up with one more idea. And the idea we need is that no slip constraint we just talked about. Right? A no slip, in fact, gives me that A equals R alpha. We now have 3 equations. Oops, let me box that. We now have 3 equations and 3 unknowns. Our goal here is to find the acceleration. I should have mentioned that at the beginning. We're trying to find the acceleration A. Our goal of mass. Okay. But at this point, right, we've done all the physics. At this point, it's algebra to solve for A. I'm going to erase the board and then just step you through the algebra, and then you'll get to think about how to extend this theory to some of the effects we haven't thought about. Okay, so just to recap, we have 3 equations from Newton's second law applied to the hanging mass, the rotational analog of Newton's second law applied to the pulley, and our no-slip constraint. We want to solve for A, so we want to knock everything else out of the system. 3 equations, 3 unknowns. You know how to do this. Bunch of ways you could do it. I'm going to propose to knock out alpha by combining these 2 equations here. Right. So I can solve, right, 3 gives me, right, alpha equals A over R if I divide both sides by R. And if I go and plug that in here, I get I alpha, which is now IA over R, equals R times my tension T. We've got to use all three equations, so we'll need to bring in equation 1 at some point. This has got a tension in it, right? And we want the accelerations. We want to eliminate that tension. I could do that by solving this here for my tension, shoving it in there. So solve for T. And that gives me, by dividing by R, I get T equals I, oops, that's a linear acceleration, not angular, over R squared. And now plug into 1. Okay. And that gives me minus MA equals this I A over R squared minus mg, and now we just solve for A. Several ways you could do this. Maybe for me the easiest thing is I'll shove the mg term over here, I'll shove this term over to the right, so I get mg equals I A over R squared plus M. Okay, you see now how I've got all the A's on the same side of the equation. I can factor the A out of this, right? So I get A times the quantity I over R squared plus M, right, equals mg. And then when we're done, I'll just erase from the top. We'll be able to just divide both sides by this entire thing down here, and we'll solve for A. So, rolling over from the bottom, we end up with A equals mg over that entire thing, I over R squared, or actually I'll write it just for convenience. I'm actually going to write it as M plus I over R, that should be in R squared. Let me rewrite that a little more clearly, R squared. Okay, so let's start to think about this. So I can do a little bit of algebraic simplification if I just multiply by 1 over m over by 1, that is. So I'll simplify mult. Okay. If I do that, that lets me simplify this a little bit. And that actually gives me the form that I want to think about. So that cancels out the g and the m in the numerator, leaving me with g. Cancels out the m in this term, and then I get 1 plus I over mr squared. So this is our idealized model with no friction. This was a little bit involved, so let's think about what happens in some important limiting cases. So first, let's think about what happens when we have a really big M. So if I hung a really heavy weight off the end of the pulley, off the end of the string, and large here means, right, this quantity I over mr squared is unitless because I can only add quantities with the same units in the denominator. So what this really means is m is much larger than I over r squared. For large M, right, For large m, right, I over mr squared is going to have, mr squared, the denominator of this little bit, I over mr squared, this denominator is going to go to 0, right? Sorry, the denominator is going to get big, so the fraction is going to go to 0. And so what happens is that the acceleration approaches little g. That kind of makes sense. If I have a massive thing on the end of my string, probably the pulley shouldn't really matter. The opposite limit of small m, so if m is much less than I over r squared, or if equivalently the pulley has a really big mass compared to my, compared to my hanging mass. If you were, let's say I use like a big steel, weight disc barbell thingy from the gym, and I hung a little 10-gram mass off of it, you can probably imagine I'm not going to get a big acceleration. So let's see what happens, right? If I have a small m, right, then I over mr squared is going to be really big, right? If I send m to 0, right, this is going to blow up to infinity. But if I have this, infinity plus 1 is infinity. If I have this thing in the denominator, right, I have acceleration equals g divided by some massive thing, which means my acceleration goes to 0. So that also appears to make sense. And in the middle, you sort of have a continuous transition between this behavior, so no acceleration for small m, and approaching g for large m. So that's sort of the basics of the theory behind the idealized version of the falling mass and rotating pulley. On Thursday, we'll think about some of the other things that might happen. You'll work on extending this theory to incorporate some other effects, things like friction, and then we'll think about quantifying the things that we can quantify in order to be able to do this experiment. See you next time.